Okay, let's start from this, the energy momentum tensor. That is a tensor that is conserved, if you look at it, as four different currents. That means this equation is very similar to this one. Okay. It's very similar to this one, but there are four more indices, and these are space-time indices. So we derived the other time that this conservation law, every time we have four currents, or more than four currents, like in this case, that are conserved, they derive from a symmetry, and the other time we explain the nature theorem that says that if you have a symmetry, then you have a conserved quantity. The conserved quantity is always the integral of the space of the time component. Okay, and in this case, for the energy momentum tensor, which was the symmetry? The symmetry was space translation, where epsilon mu is an infinitesimal translation. So if this is the symmetry, then we find out that the energy momentum tensor, we write it with lower indices as the following form: G mu nu, this is the Lagrangian density, plus the sum over all field. Sigma is not a space-time index here, but is it's something that labels the various field. Okay, so we sum over all the fields entering our system, and this is the conserved quantity, and I think we prove the conservation of that, right? Okay, now let's apply this to the Schroedinger case. That means we have first to find which is looking at the wave function. So you have the usual Schroedinger equation that we can write as an Hamiltonian, operator Hamiltonian, that is this derivative, second derivative plus the potential. V is the potential on psi. We want to derive this from a Lagrangian, from a variational principle, and it's easy to see that the Lagrangian is the following: minus h over 2m gradient of psi star, gradient of psi, minus h bar over 2i psi star d psi dt minus d psi star dt psi minus psi star v psi. Okay? Now, so the point is, can we, looking at this wave function as a field, can we derive the Lagrangian, can we derive the equation of motion from that? So let me just yes.
Why is the reverse not true?
Oh, the inverse is not true because there are some symmetry that some conserved quantities are called accidental conserved quantity that are not related to symmetries. Okay, so there are some quantities are conserved that are really not due to symmetry. So in one direction it goes, in the other direction it does not go, because there are cases. So it's not you know, we did not even go in the detail of proving the theorem. Just is a statement for the moment. That means I will. The reason is that there are quantities that are conserved but are due to not symmetry. But there are very few cases, so you can take in both directions. There are very few cases and on very particular things. And okay, but this is not the main. Okay, so let's write here that the energy momentum tensor T mu nu G mu nu L plus sum dl Well, you complained for my handwriting and that to type everything. Next time I make you type all your homework. So I appreciated that you did with LaTeX because it was a lot of work. I mean, it took me 3 full days to correct. I'll give you at the end of the thing your thing. I mean, at least your name, you know. I mean, can you print your name? Print means write in normal letter, not. If I write like that, my name, I'm sure you don't understand. And many wrote their name and first name like that, and all of you have 3 words in your name, or 4, even some. So imagine, I mean, I have corrected, but at the final, if you do something like that, I give 0, okay? No justification. I don't understand, 0. Cancel, throw away. I mean, I do it, okay? I have done. In Trieste University, you can ask. I have done. Just wrap it up and throw it away, 0. Okay, so because I did some work to put my lectures and I have no time at all because they asked me in an emergency to teach this class, and I was not due to teach this class. So, and then if I have to waste 3 days to correct 15, 3 days, 3 full days. I mean, you understand? So, okay. And then, you know, this time what I did where I did not understand, I was mild and all the grades are good. The lowest, those who got the lowest is 40 points over 50, but it's the last time I do. Okay. Okay, so now we will show, or did we already show that from this Lagrangian? We did, okay, so I will skip this. From this Lagrangian you can derive these. And now we can also we can derive let's for example here for example if you want to put one index up and one down, then these become a delta mu nu, and then these become a delta mu nu. This is up and it goes down, and this is up, okay. And the sigma in this case, psi sigma, stays for psi and psi star. So the sigma indicates, in this case, the 2 fields that enter. So for example, let's go and calculate the energy. Well, first of all, let's look from here if we can go and calculate the Hamiltonian density. The Hamiltonian density associated to the Lagrangian is like for the point particle, it will be a momentum that I call pi sigma. Psi, first of all, let's introduce the momenta. The psi sigma are nothing else than dl d psi dot sigma. Okay, and there are 2 psi, one associated to psi and one associated to psi star. Then you define the Hamiltonian density as sum over the psi sigma, psi dot sigma minus L, like the normal Hamiltonian, momentum minus P Q dot minus L, okay? And then if you do this calculation and keep account of the various things of the momentum and so on, somehow magically the momentum disappears from here. And the reason is very simple. If you take these 2 and do the calculation, you get I over H psi star and minus I over H2 psi. These are the two momenta. And then because there is this that actually we call a constraint, there is a cancellation, and the Hamiltonian turned out to be minus H bar over M0 gradient of psi star minus 2I H psi star V psi. So this is the Hamiltonian density associated to the Schroedinger Lagrangian. Now, okay, that is one point. Let's calculate, for example, the density, the energy density of this. Let's calculate T00, and then we will see what it is. So let's apply, let's take these, and then we have 0, 0, so we have minus L plus sigma dl d psi sigma dx0 d psi sigma dx0. Okay, now if you do, you get the following expression: h squared over 2m0 gradient of psi star times gradient of psi plus psi star v psi. Okay, there is something that does not work. Yeah. So this one I can write as the following: minus I minus I, let me see, minus I, if I multiply by h, I have h squared, and then, so, h I 2m is there, so by 2, just a moment, h squared, this is plus I, so is I t 0, 0. Okay, so you can, if you look at that one and look at this, there is this relation between the two. There is some factor of I that is not correct, but okay, don't, let's not worry about that. What is interesting, in a modulo sum factor, the Hamiltonian density and these objects are related, modulo sum factor of I. But what I want to show to you is another further things. Let's remember this object, this operator that is the first quantization operator, and then you know, from the fact that d mu, t mu, nu, d mu, t mu, nu is conserved, from this fact we know that if we take these are 4 currents, so if we take this object and integrate over d3x, okay, this object is for sure conserved. Actually, what is conserved is these 4 objects, okay? But anyhow, let's take the 0, 0. Let's take the 0, 0. For sure, it is a conserved quantity. Let's look at the expression, and if you look at this expression, just put it in, and you get psi star h psi. This is the, let's call this object, okay, let's call this object, I don't know how to call it, but let's call it in this manner, okay? So we know it's conserved, and look, it can be written in this manner using this operator, this first order operator. So there is a rule that every time you see a wave function as fields, even at the first quantization level, if you look them at fields, then the total energy, that this is the total energy, is related to the Hamiltonian of first quantization in this manner. You sandwich the Hamiltonian on this. And you know that this, if you look at first quantization, is the average value of H, right? And so this is the energy. Okay? So you see all these fancy things, but for the Schrödinger things, it boiled down to be a very simple thing. There are other quantities that are conserved, for example, the T0I, okay? Also these, if you integrate D3x, these are three quantities that are conserved. And this is, while this is the energy density, this is the current, the current associated to the energy density, okay? And so it's called also energy flux, and also this is conserved. So we have the energy density that is conserved. We have the flux that is conserved, and we have also, we can exchange the, so we also have these that are conserved. Okay, so this is the energy flux, and this is the momentum flux. It's called momentum flux. We will not enter into the details of this because this is not the role of our, this is not the role of this. I just wanted to introduce this fundamental concept that any wave function, any equation that control the behavior of a wave function, be it non-relativistic like the Schrödinger or the relativistic like the Klein-Gordon, you can look at the field, at the wave function as a field, and you can derive a Lagrangian density out of which the equation of motion can be derived. Okay, in most cases it's been done for the Klein-Gordon, for the Schrödinger, and so on. Now, once you have a Lagrangian density and you look at this as a field, okay, you can derive an Hamiltonian density, and this Hamiltonian density associated to Lagrangian is related to the T00. The T00 is the 00 component of the energy momentum tensor. The energy momentum tensor has this general expression, not just for the Schrödinger. We derive it in general, where sigma is the fields that are there. We have two fields there, psi and psi star, because the wave function is a complex quantity. And if you build the T00, you find out that the T00 that is related to that, to the integral of that quantity. Okay, so maybe I should not put, because at the end this is a number, so it's the same as that. This is like the Lagrangian, the Hamiltonian density. And what you get is that the Hamiltonian density derived from the Lagrangian density or from the energy momentum tensor can always be written as the sandwich of the usual Hamiltonian operator of the Schrödinger first quantization, sandwich between the psi, but this is nothing else than, so basically, that the average value of H on the wave function. So the T00 is related to the energy density. Okay. Now, let's go back to the Klein-Gordon now, and we will now continue with the Klein-Gordon. This was just, let me see what if I have something left to do. Now, what we had already proved is that the T00 is related to the energy. We did when we look at the Klein-Gordon and took the free wave and proved that it's equal to the energy. We did that, okay? So that was one manner to see that the T00 is related to the energy, and that is what we already did. We wrote down also the Lagrangian from which the Klein-Gordon can be derived. And then we did the energy momentum tensor a few lectures ago. and then we said, okay, let's look at the t00. We wrote down the t00 and inserted the wave, the free waves inside the box, and we found that the t00 is related to the energy. Okay. Okay. We did this non-relativistic just to develop some tool. Now let's go back to the. Let's go back to. Can I cancel? I'm just following the book, and I'm not really adding anything except comments. So my advice to you is listen to the comments, and if you don't understand my English, just ask me to repeat, because the only things that I add to the text of the book is some comments. Okay, some comment just to indicate what you have to stress and what is important and what is not important. The book sometimes overlook at something, or it does not stress enough something. So, I mean, usually when I stress something, I turn around and tell, look, this is important for that and that. That one is the only thing that you should really write a note on your book note, but not copying from the blackboard, because I'm just copying from the book. So it's just a copy of the copy of the copy. And, you know, usually, you know, all the mistakes in the universe are done by copying. So the DNA, basically, we develop cancer and all these kind of things because in copying the DNA, some mistake gets in. So don't copy of the copy of the copy because... Okay, now, what we will do is, we will ask, the question we will ask is, this is very important because somehow the book does not underline it enough. Is it possible to bring the Klein-Gordon equation in a form that is first order in the derivative? You know, all the problems, if you remember, all the problem of probability interpretation of the Klein-Gordon came from the fact that the Klein-Gordon is second order in the time derivative. So, well, let's see. It's not that we want to solve those problems, but let's see at least formally if we can bring the Klein-Gordon into first order derivative. First of all, as the Klein-Gordon is second order, you have to specify both psi of 0 and psi d psi of t at t equals 0 to solve the equation. It's second order, so you have to give two initial conditions. That means these two quantities are totally free. You are free to use them as you like. So let's define the following two quantities, phi and chi, two new fields. These are two new fields. So this is a Greek letter called chi, and in LaTeX the command is to get this letter, okay? And this is another Greek letter, you know better than me, phi. The command is this, just in case. So let's introduce two new quantities, phi of x, chi of x, related to psi in the following manner. Psi equal to phi plus chi, and IH d psi dt equal m0 c square phi minus chi. This is just a definition of phi and chi. Remember this, the book does not, the book is rather confused, I would say, on this point. So if you copy these, just put in definition of phi and chi. Why I can give a definition like that? Because these are totally free. Psi and the first derivative are uncoupled. They are not, I mean, if I give psi 0, it's not automatically given the first derivative because the equation is second order, okay? So that means this does not determine this. So these two quantities are totally independent, and then they are also independent at later time. So I can give, these two quantities are totally independent. So I write these two quantities, forget about the IH. I write psi and this derivative as a function of this. You can ask, why did you put these and IH? Just for convenience. I could have put 1 and 1, okay? So if you don't like, you can put 1 and 1, but for convenience in the sense that then the equation for phi and chi will be very simple. So the first thing is we introduce two new fields that are related to the old fields in this manner. And they are also complex fields, okay? Because we are putting two new complex fields, so altogether there are 4 fields equal to two old complex fields, psi and psi star. You can say, why do you, you can do this because I have 4 independent fields. The psi and the derivative are 4 independent fields. 4 because each of them is complex, okay? And I am equating these two fields that are independent to two new fields, okay? So this is a definition. If you look at things the other way around, look at these things the other way around. Don't look in this manner, look that phi plus chi is equal psi and so on. Or if you want, you can, for example, this is a definition because, you know, it's easy to see that if you do the sum and the difference between these two multiplied by proper factor, you get that phi is defined as 1/2 psi plus 1 over m0 c square IH d psi dt, and chi is defined as 1/2 psi minus 1 mc square IH d psi dt. Okay, so if you don't like to look at this as a definition, you can look at this as a definition. How do I got this? I just multiply by proper factor and then add and subtract these two, and you get this. So this is the definition. It's just that it's a hopeful definition, but this is the definition of these two new fields. Sorry that I insisted on that, but this is rather important. Now, let's do now the following. Let's take the first order derivative of this left-hand side. We know that the psi satisfies the Klein-Gordon equation, okay? But we also know that phi has this definition. So let's do the first order derivative. So from here, I do now the first order derivative. So IH bar d dt of this quantity phi and chi. So I do the first order derivative, then I do on the right hand side, but I know that this satisfies the Klein-Gordon equation. You understand what I did? This is the definition of phi and chi. I apply the first order derivative for phi and chi. I propagate it to the left, to the right. And then psi, I know that which equation it satisfies. I know this satisfies the Klein-Gordon equation, and I replace with the Klein-Gordon equation. At the end, I replace psi with this combination, phi plus chi, so that I have an equation only in phi. The result of this is the following: IH d phi dt minus h square 2m0 Laplacian phi plus chi plus m0 c square phi IH bar d chi dt equal, sorry, here is equal minus, equal plus. Now, this is what we wanted to achieve. We wanted to achieve in two different fields a first order equation. These are first order equations. But which is the price we pay? They are coupled first order equation. You see there is a chi here. I could not write this as an equation only of phi. There is a chi here. And vice versa. The equation for chi contains a phi. So these are coupled first order equations. And they are equivalent to the Klein-Gordon. Why? Because if I go back, which ingredient did I use? This is the definition, or this is the definition. I inserted, I said I took the derivative with respect to time, then the derivative with respect to time of these two goes into here. Here I use the Klein-Gordon, and I get these things. So the only ingredient I got is basically the Klein-Gordon. Now, you don't believe that this is equivalent to the Klein-Gordon? The only ingredient I have used is the definition of phi and chi, and the Klein-Gordon equation on this. But now, if you don't believe, let's from this equation go back and get the Klein-Gordon, okay? So that is what we will do. For example, let's add these two equations. If we add, here there is a plus, there is a minus, and there is a, here there is a minus, here there is a plus, these two pieces goes away, and we get the following things. IH ddt phi plus chi equal m0 c square phi minus chi. You see, so adding the two, we got back this. And this was the definition, because if you remember, this object is psi, so we got d dt d psi equal m0 c square phi minus chi. So adding the two, we got one of the two definitions. This is not, of course, the Klein-Gordon equation, but it says that these two equations are related to that, of course, because we derived them. But you understand, so we have add. If we add the two, we get this, and this is nothing else than the second definition. Now let's subtract the two. So adding, we got the first definition. Let's subtract the two. So let's subtract the two equations. If we subtract the two equations, subtraction, I h bar d dt phi minus chi equal minus h square over m Laplacian phi minus chi, this Laplacian, plus m0 c square phi plus chi. I have subtracted the two, so I got this piece. I have subtracted the two, and then I get a 2 that cancel these two in the denominator. And I get, if I subtract, I should get away a chi. Why do I have it? I have because I made a mistake here, maybe. No, it's okay. Right. Okay. Now we have got this equation. Now let's use this. Every time I have phi plus chi, I replace with psi. And every time I have phi minus chi, I replace with the derivative. So here, I replace with the first derivative of psi, more or less, modulo some coefficient. Here I replace with psi, here I replace with psi. And what you get is, at the end you get minus h square over m0, 1 over c square, the second derivative of c with respect to t square, minus h square over 2 m0 Laplacian of psi plus m0 c square psi. Actually, you don't get this. First you get, let me go here. So I am subtracting. Now I am replacing this with this and this object with that. Then from here, you get the following expression. You get I h bar d dt I h bar m0 c square d psi dt equal minus h square over m appellation of psi plus m0 c square mc. And this is nothing else than the Klein-Gordon, because simplifying things, you get the following expression, simplifying the various quantity. Okay, so you see from these two first order uncoupled equations, by subtracting them and using the definition, I got the Klein-Gordon equation. So these two are equivalent to the Klein-Gordon equation if you use this definition. This is crucial. Huh? If you use this definition of phi and chi, these two equations are equivalent to the Klein-Gordon equation. But the price I pay is this. Okay. Now, one of the homework, of the new homework, that I think I dictated already the other day, is exactly this derivation from that to get to this. That is very simple. It's just the details are not worked out in the book, but they are just algebraic detail. Now, these coupled, so these two coupled differential equation, coupled because the phi and chi, let me write here all the things I need, and on the rest of the blackboard I will write. So these two are equivalent to the Klein-Gordon second order equation. We proved that, and the definition is psi equals, so this definition, phi plus chi, and I h bar d psi dt equal m0 c square phi plus chi, phi minus chi. Okay, so this is the definition of these two new fields. These are the two new fields. Thanks to these fields, I can write the Klein-Gordon as a coupled. Now, there is a manner to write these two equations in a more compact, formally, in a more compact way. Yes, there is. So remember that we are still answering, is it possible to bring the Klein-Gordon equation in a form that is first order in the time derivative? There is. So the question is answering the positive. But now I don't like this. There is a manner to write them in a more compact form. Yes, there is. If you introduce the following object, like, you did the Pauli equation when you had spin, and you remember that a particle with spin in a magnetic field, the Schroedinger equation becomes the Pauli equation, and the Pauli equation has two components. So let's do the same. Let's introduce this new field, psi tilde, that is a two-component field that has, so basically is a vector whose upper component is phi and the lower component is c. And then let's introduce the usual Pauli matrices that the convention I use, I think, is the standard one. And these tau have the usual property that you know very well. And then it's possible to write this as one equation for this strange object. And the equation is the following. I can write that two equations, these two equations. So now I'm rewriting these two equations. These two can be written in the following manner. I h bar d psi tilde dt is equal to some strange Hamiltonian that we will call in this manner psi tilde. So take this object, and this now I will show to you, I will give a definition of this, is equivalent to this. Now, what is this strange Hamiltonian that is there? You see how much it looks like the Pauli equation? First order equation for a two-component wave function. Okay? You have done the Pauli equation? I mean, Pauli equation, it means the following. If you have if you have a particle that has also spin, then as it has also spin, the wave function is, you have the spin space tensor product with the wave function space. Okay? Then this object, the spin is 1, 0, 0, 1, or linear combination of that, come out to be something like this. This object, if you do a tensor product between the spin space and the wave function space, is a wave function that has two components, okay, just basically. And then there is an equation of motion for these when you have a spin and the interaction of the spin with the magnetic field. This is called Pauli equation. I advise you to just go into some books on quantum mechanics or look. You can look in Google, and Wikipedia will give you the things. Now, what is this Hamiltonian? This Hamiltonian is not so nice looking, but you see that this one looks very much like the Schroedinger equation, right? This is a two-component object. This, now you will see, as this, there are two wave functions here, because it is an object made like that. The Hamiltonian also will have, will be a set of two Hamiltonian. In fact, the Hamiltonian turns out to be tau 3, the tau 3 of Pauli, plus I tau 2 p square over 2 m0 plus m0 c square tau 3. Okay, and these things, if you want to write in component, is 1, 1, minus 1, minus 1. This is an operator, okay, is an operator in wave function space, plus 1, 0, 0, minus 1, m0 c squared. You see, the Hamiltonian is an operator in wave function space, but is the set of two, okay? Because you are acting with this Hamiltonian on a wave function that has two components. So also the operator must be at least two, okay? Must be at least two, actually it must be a matrix. This object is the tensor product of a 2 by 2 matrices related to the Pauli matrices and the usual operator on Hilbert space, okay? So it has this form. This is an operator in the normal Hilbert space, so it acts on wave function. And then you have to multiply it by this, because this operator will act, this one will act on the same way on this and this. But then how they get mixed up? You see that there the phi and chi are mixed up. They are mixed up by these matrices. Okay, so how do I apply? I apply this to this, but what does it mean, this? It means this phi and chi, and then this now I see that is differential operator multiplied by a matrix, so there are matrices acting on phi and chi, another matrix acting on phi and chi. Okay, so you can multiply this operator inside here and you get p square here, minus p square here, and minus p square here. Okay, so that means these contain 4 times, I mean, it's a 2 by 2 matrix, so there are 4 times these things. Is it clear that? Because it has to... Okay, so this one, if you want, can be written in the following manner. This h hat is p square over 2 m0 p square over 2 m0 minus p square over 2 m0 minus p square over 2 m0 plus m0 c square 0, 0 minus m0 c square. So this is this Hamiltonian, and it has this form. You know, now these are operator, and they act, each of them acts on phi and chi. So I apply these acting like a row on the column phi and chi. This, I mean, try to get familiar with this because the book, again, this is a point to make a note. The book is not so clear what does it mean, this object. This object means these act on the space-time part of the wave function, and these act on the fact that there are two components. So now this, you apply, this object now you apply on psi that is made in this manner. Now there are nice things about this Hamiltonian. This Hamiltonian has this awful form. It's easy to see that it satisfies the following things. If you do 2 times, multiply this Hamiltonian 2 times, you get that this is equal to c squared p squared plus m squared c4 multiplied by the identity operator in 2 by 2. That means 1, 0, 0, 1. Okay, but this is the usual Klein-Gordon equation. You see, so somehow is the Klein-Gordon operator. So somehow this is something like the square root of the Klein-Gordon operator. We will find out later on that there is a better way to do the square root. But this operator done it twice give me the Klein-Gordon equation. Please. Where? This one? Yeah, there might be some. Just check, okay? There might be some T3 plus I2, T3 plus I, T2. So I have I minus I square, I get plus. Then I have 1 there. Then I have I and I get minus 1. No, it should be correct.
Yeah, okay, let's see there. We have a minus sign. Okay, let's see the equation.
I mean, that these things does not reproduce that one.
Yeah, we have, okay, yeah.
That means here there should be a minus.
Yeah, here they are both plus, you see.
Here they are both plus. Okay, just check, okay, I just wanted to, I don't want to waste time into this detail. Please do check, because, you know, this is the best homework you can do is that redo the calculation in detail, okay, and see if there is any. There are a few mistakes in the book that I checked last year, but it's not important. Anyhow, it can be written in that manner. It might be that the Hamiltonian can be written in a different way. Now, there is a nice thing also is that if this is the Schroedinger, if this is the Klein-Gordon equation, is the Klein-Gordon operator, then we can do the following things. This is the equation. It means IH ddt minus H tilde psi tilde equals 0. This is the things. Let's apply to this equation. I can always do the same operator again. So I apply this operator again on this. So basically I get, so this is the equation, this one written in another manner. I apply this differential operator on this. As all this is 0, also the result is 0. And what you get is, if you apply this operator on that, you get minus h squared d dt squared minus, actually, h squared c squared minus m0 c squared on psi tilde equals 0. You see that there are no Pauli matrices anymore, so I have applied these on these, and I have used the fact that this object is basically the Klein-Gordon operator. Then I have the second derivative, and then I have the derivative applied to the first order things, but so this is. So you see that each, now as there is no Klein-Gordon, it means that this object, sorry, there is no Pauli matrices. This means the following. That means phi and chi independently satisfy the Klein-Gordon equation. Okay? So I start from this, I apply this. I know the fact that when I multiply two of these Hamiltonian, I get the Klein-Gordon. So if you go on and do the calculation, you get these things. Now, you remember that the two important quantities in the Klein-Gordon were the charge density, rho, and the current density. Now, can it be written in this formalism using these? Because we have to write not only the Klein-Gordon, and we have proved that these two, or this or this, is equivalent to the Klein-Gordon. We should try to write also the normal rho. For example, the charge density. Can we write the charge density using this psi tilde? The answer is yes. So let's remember the form of the rho tilde. Rho is IE h bar is the electron charge 2m0 c square psi star d psi dt. This psi is the Klein-Gordon one, not this psi tilde, okay? This is the one component things of the Klein-Gordon, okay, is this. Remember the definition, minus psi d psi star dt. Now, the question is, can you write these using those two fields? Yes. Or using these? Yes. It's possible. For example, if I use d psi dt and replace with these, and so I can do the following. This is equal E m0 c square to m0 c square. I use now psi star phi minus chi. I have used the definition. And then I have psi, and then I have the definition of the other. I take the complex conjugate, so I get a plus here, phi star minus chi star, and I have some coefficient in front, that is this. Now, replace phi with the, now this object is nothing else than phi star plus chi star. So do the calculation. So I have replaced these with modulo some coefficient with these using the definition. I have replaced these using the definition with these. Then I replace these with these and these with these. And I go on, I do all the calculation. At the end you get E phi star phi minus chi star chi. This is the charge density written in terms of the new field phi and chi. Question, can I write also as a psi tilde? Yes, so we have proved that this object is E phi star phi minus chi star chi, but this can also be written as E psi tilde dagger tau 3 psi tilde. Okay? It's easy to see. You see there is a minus here. So this is a very compact manner to write the charge density. And the same for the current density. The current density was a little bit more complicated, and it will be more complicated even in the two-component formalism. So sometimes in other books you hear about the two-component formalism for the Klein-Gordon. It means this, the two-component formalism. Okay, now let's do the current density. The current density was defined EAH bar to M0 psi star gradient of psi minus psi gradient of psi star. Now, question, can it be written in terms of phi and chi, and then in turn be written in terms of psi tilde? Yes. I will not do the calculation, I'll just give you the result. The result is really a little bit complicated. So I am writing this in terms of the two-component formalism, that is a long expression, and then to compactify it, I use these things. Can I do? Yes, I can do, and the result is this. I psi tilde dagger tau 3 times tau 3 plus I tau 2 gradient of psi tilde minus gradient of psi tilde tau 3 plus I tau 2 psi tilde. Okay, it's a little bit more complicated. Now, one last question one can ask, well, the original field I started from was normalized. Are these normalized too? No, they are not. They are linked to the normalization of these. Oh, now we will go and see how they are linked. Well, if you remember, so it's clear we rewrote the charge density and the current density in terms of this new variable. Now we will look at the normalization. The normalization was somehow of the psi. Remember that this is the charge density. And we know that when we have the charge density and integrate over d3x, we should get the charge, that is E. But you remember that it was not positive definite. It could be either plus E or minus E. So this is the thing. But let's remember the expression that I cancelled of rho prime. The expression of rho prime was phi star phi minus chi star chi. Okay, so there was a minus. So what you get is that the following things: phi star minus chi star d3x is equal to plus minus 1. Okay, there is an E. Rewriting the rho in terms of phi that I did before, there was an E that cancelled with this E. So this is the normalization that these objects satisfy. And it's not really a normalization, but so remember one question. Well, the other things is this. Last year in the final exam, I wrote down not just problems, but I don't remember if last year or the year before, but theoretical questions. So one theoretical question could be, could you bring the Klein-Gordon equation into first order set of things? So you just have to remember the things, even if you don't remember by heart the coefficient. You tell me which is the strategy, roughly. Say there is a coefficient that I don't remember, but I want that you understand the strategy. So one question could be, from the Klein-Gordon derive a first order formalism, and you have to tell me which are the steps, even if the coefficient you don't remember by heart, because you don't have much time, but just tell me the strategy. So I have not, of course, prepared yet the final exam, but there can be theoretical questions. So that is why I ask you, redo the calculation, okay, to check the plus and minus 1. I made mistake at the blackboard and so on, but it's just because it might be very helpful for the oral exam. Okay, so this is the normalization of the phi. So if one question I ask is the psi normalized? Yes. Is the phi and chi normalized? Well, their normalization is linked to the normalization of the psi in the following manner. Okay? And you see immediately that, for example, as they carry charge, the plus 1, it could be that we don't have this component and we have only this and we have a plus, vice versa. The minus 1 might come from the fact that this is normalized and this is 0, and then you get the minus 1. But anyhow, the space integral, let's say, of the rho and the chi are related in this manner. If I ask you why they are related in this manner, then they derive from the normalization of the psi, that the normalization of the psi in turn gives you this, that the integral of the charge density is plus or minus E. Now, one last thing, let's see if that equation that we derived before for the psi tilde can have, so the equation was A d psi tilde dt equal H tilde ct. This is the Klein-Gordon equation written in that manner, okay? And the question is, can we have first order, now we can cancel, can we have plane wave solution? And if we can have, this is very important things, can we have plane wave solution, and if we have the energy and the momentum are related in some way? So the question that we are asking is, does this equation admit solution of the following form? So the question is, as this, among its many solutions, also this solution, psi tilde equal to some, well, it's phi and chi, we know from the definition. It will be a normalizing coefficient plus some initial things, and then, so this is the initial things, this is the things at t equals 0 and the x equals 0, exponential I h bar px minus et. So we are asking ourselves, do solution of this form that are plane wave in x and t, these are plane wave in x and t. And of course, this object can depend on P and E. Are just the phi at time 0, but in principle they can depend on P and E. So the question that we are asking is, are there solutions of this form, like plane wave solution? So you see, chi 0 and phi 0, it means the phi and chi at time 0 and at x equals 0. And then the space-time part is a plane wave. Okay, so we ask ourselves if there can be solution of this form. Okay, let's remember the form of H. You remember the form of H tilde? H tilde at the following form: 1, 1, minus 1, minus 1, p square over 2m square plus 1, 0, 0, minus 1, m0 c square. So let's take and bring this into this, and let's see what we derive. You understand what I mean? I am putting in these things over there and see if this can be a solution. What does it mean? Is it possible? Where is the freedom we have? The freedom we have is in the initial things and in this. So is it possible to find an A, a phi 0 and a chi 0 such that that equation is satisfied if the space-time part is just this? This is just the space-time part, okay? There is, you see here, there is no space-time part. So when I say it's a free wave, it means from the space-time point of view, it has this behavior. Here is only some function of P and D. This I have the freedom to let, but this is basically, this first part is A and T. This A is a normalizing factor, okay? So let's put in and see what happened. Well, when I take the derivative with respect to t, where do I hit? I hit here. So I'll bring down an e. So so now we plug that in, and what we get is the following: E phi 0 chi 0 equal 1, 1, minus 1, minus 1, p square over 2m0. This is not the operator anymore. Sorry, this is the operator. This is the operator. This operator is ddx. It will act on this and bring down this part. Okay. So while this is the operator, this is this number. Okay, modulo of course. 2m0 phi 0 chi 0 plus 1, 0, 0, minus 1 m0 c square phi 0 chi 0. Okay, so I have plugged in this and I get this relation. Why? On the left-hand side I have the derivative with respect to t, so I bring down an e, and then I multiply. There is a also here, but there is a here, and they cancel. Okay, so this a normalizing factor does not enter here because they cancel. Then I take the right-hand side. This contains the second derivative with respect to x. I do the second derivative and I bring down a p square, but with this matrix in front. And then I have phi 0, chi 0. You see, I have seen many doing in homeworks and so on, that they cancel this. No, you cannot. This is a 2 by 2 matrix, it's not identity. A I could cancel because A is a number in front of everything. Okay, so these actually are two equations for phi 0 and chi 0, and they are coupled equations. If you work them out, so let's do this matrix calculation, and you get two equations. You get E phi 0 equal p square over 2m0 phi 0 plus chi 0 plus m0 c square phi 0 E chi 0 equal minus p square 2m0 phi 0 plus chi 0 minus m0 c square chi 0. Now you see, these are not anymore differential equations. These are algebraic equations for this unknown, A0 and chi 0. And they are coupled equations. These are two coupled algebraic equations. Remember that means if this is satisfied, then this is satisfied. But if this is satisfied, it means this solution is solution of that. Now, question. Is this satisfied? Well, we have to find the phi and chi. And this, we can write these. The unknown quantity are phi and chi, so I can write this in the following manner. E minus p square over 2m0 minus m0 c square phi 0 minus p square over 2m0 chi 0 equals 0. And p square over 2m0 phi 0 plus E plus p square over 2m0 plus m0 c square chi 0 equals 0. The unknown are these. These are 2 by 2 matrix. The unknown are phi 0, chi 0. Now, when will this have a solution? This is an eigenvalue problem. It will have a solution when the determinant of the coefficient is 0. Okay? So, for that equation to have a solution, you have to have the determinant of the coefficient. The coefficients are these. Must be 0. So, it means E minus p square 2m0 minus m0 c square minus p square 2m0. Take the determinant of the coefficient, and the determinant must be 0. Otherwise, you don't have solution differently from the 0 one. So for sure, 0, 0, if phi 0 and chi 0 you put equal 0, it is trivially satisfied. If you ask, when is this a solution different from 0, 0? When the determinant of the coefficient is equal 0. Work this out, and if you work this out, you get that this is satisfied when E square is equal to P C square plus M0 C square. But this is the famous mass-shell relation. So what does it mean? What does it mean? It means, look, the free wave is a solution, but only if E and P satisfy the mass-shell relation. Okay, so that is one important thing. That means we are not in contradiction with the Klein-Gordon. We can say that of that equation, first order equation with the psi tilde, it has a free wave solution if E and P satisfy this. Then the next thing is to determine phi 0 and chi 0, because that are the eigenvalue. By the way, here there are two solutions. Okay, so the first things we have determined is that, let me, okay. Now, okay, here there are two solutions. One is EP is equal to plus square root of p square c square plus m0 c4, and this is the first solution. The other solution is EP minus p square c square plus m0 square c to the 4. So there are two cases. So now I plug in this expression that I know that with one of these two expressions, the phi 0 and chi 0 are different from, can be different from 0, and let's find them. These are now the eigenstate, you see. Phi 0 and chi 0 are the eigenstate of this matrix. Okay, so it has to satisfy the Klein-Gordon, the mass shell duration for the free wave to be a solution. That is one important thing. And also this is not stressed enough in the book. I mean, it seems you get to the mass shell relation and it does not make any comment. Well, of course, the comments are trivial, but it means the free wave is a solution of the first order equation only if EMP satisfies the mass shell relation. Now let's choose the positive plus, okay, let's choose the positive one. Then we have to find the two eigenstate. And what happens is, you know, like in all cases of eigenvector, you have, because this determinant was 0, that one you can choose as you like, and the other you get. So we will choose as we like the chi plus. We will choose as chi plus this. This we choose as we like, and we make this choice just for convenience. Then we will get that m0, that phi plus is m0 plus EP. I put a plus because this is the eigenstate of that equation associated to this now, why I get these things? I said, let's choose this for free, and let's choose, I mean, there it says, look, one of the two is free. Those two equations, as the determinant is 0, are not independent. One is linearly equivalent to the other, so there is just one equation, actually, not two. So you can choose. So I choose chi 0 in this manner, and I get phi 0, because, you know, if you look at this first, if you plug in for chi 0 that expression, you get for phi 0 what I have up there. Okay? So it's derived from this. Now, what is left? Remember, the solution was psi tilde equal a phi 0 chi 0 exponential IPX minus ET. So there is A to be determined. Well, A you determined by normalization, but which normalization? Remember that the normalization was phi minus chi star d3x, and these are the solution, this chi solution, this plus energy solution. Remember, the plus energy solution, when we interpret rho as charge density, are associated to the plus and plus charge, so is equal to 1. So if you plug in that expression, so plug in that expression where the phi means this by this by this, the chi means this by this by this, then you get the expression of A, and you get A plus, because here I use the plus 1, so the coefficient that should go with this is equal 1 over 4 m0 c square 1 over L cube EP. L cube is the size of the box in which we are. Okay? So now we have determined everything, at least for the case in which we choose the positive branch of the two energy. This is the expression of A plus, and we have the expression of this, and this is modulo, of course, the freedom that I have in choosing one of the two components. Now, let's do the other choice, the E minus, the E being negative. Okay, so now let's choose E equal minus EP, in the sense that we choose of the two this negative one, so equal minus P square C square plus M0 square C4. My solution I call psi tilde minus, it depends on, well, okay, it will be an A minus, then phi 0 minus, chi 0 minus, exponential EPX plus EPT, where EP is the positive part, so it becomes a minus, so EP is this things over H bar. Now I have to find again, solving that equation, the two things associated again. So the phi 0 minus chi 0 minus is the eigenvector of that equation. I have the freedom of choosing one of the two, so I choose this second one to be this. You will understand in a moment why this choice. You could have asked why you did this choice. I said it's for convenience. And now the convenience you will understand as we do the non-relativistic limit. So let's do this, and then we get that the other is mc square minus EP. You see, exactly the minus, the one associated with the negative energy, is just the upside down of these things. Now, and of course I have to determine A minus with the same things, but this time, to determine the A minus, I will use these with a minus one, because it's the negative energy. The negative energy were actually associated to the negative charge, so there is a minus here, and I get this, but it turned out to be the same. Okay. So how I got this? I got this from the eigenvalue equation with this choice that I made, and I get this. So which are the three? Let's summarize the three things. First, the free wave is a solution of the first order Klein-Gordon equation if and only if E square is equal to P square C square plus M0 C square. So that is the first thing. The second thing is the phi 0 plus or minus chi 0 plus or minus R, this one and this one. That is the two things we have realized. So the free wave is a solution of the first order Klein-Gordon equation if and only if the mass-shell relation is satisfied. Second, this phi 0 and chi 0 can be chosen as is the better expression, because actually the second component I choose as this one and that one. Third, A plus is equal to A minus and is equal to this expression here. Okay, so these are the three things we got. Now, note that phi 0 and chi 0 depends on E and actually EP, so they depend on P. So these are function of P. These are function of P, particular function of P. The important thing is now, of this free wave, if I take the non-relativistic limit, I mean, nobody can remember this expression. So one important thing is if we take the non-relativistic limit, what do we get? So I will cancel this for the moment. Just keep this. So the solution is plus, minus, plus, minus, plus, minus, plus, minus. These are function of P. And this is a function of P. And remember, we got them okay, now I can cancel. Now the next question is, can we do the non-relativistic limit of this expression? So basically, remember, we are handling now free waves. But it's not like free waves of a free equation. It's the free wave of the Klein-Gordon, where P, E, and M are related. As a consequence of that as they are related, also these are not anymore arbitrary function, but they are arbitrary up to something. The arbitrariness is only in the chi, and the phi is automatically determined from that eigenvalue equation. And that is because we got a matrix equation. We would not get a matrix equation for the Schroedinger one. We got a matrix equation because we insisted in putting first order, a second order equation was the Klein-Gordon. All this is derived from the fact that we have a matrix equation. And the matrix equation, first order matrix equation, is because we insisted in having a second order like the Klein-Gordon turned into a first order. The price we paid is that matrix equation. Then as we have a matrix equation, we end up into an eigenvalue problem. Having an eigenvalue problem, we get particular eigenstates and particular eigenvalues. Okay? So you see this one as this particular form, this embeds the fact that there are some particular form embed the Klein-Gordon character. You would not get all these in the Schroedinger equation. You understand the point? I am talking about eigenfunction in the spin space. Let's not call spin space, but in the internal space that makes the second order equation first order. This is formally, is not physics-wise very important, but formally is important. Why is important? It's important, we will stop here. We will do tomorrow, well, Thursday, the things. We will do of these, we will do the non-relativistic limit. And the non-relativistic limit will be very interesting. You will see in the non-relativistic limits, this dependence on P will disappear. In fact, in Schrödinger, you never had that things. And these things in the non-relativistic limit will become 1, 0, or 0, 1. Okay? So this will be very important. The dependence on P is just because of the relativistic character or of the Klein-Gordon character. But the non-relativistic limit is very useful because all the calculation that you will do in we will do some application, maybe I will see, but we will do the non-relativistic limit on Thursday.